Okay, so the last week, guys, I put up a few questions on the YouTube website regarding some questions on equilibrium that were a little bit left field, so not the same as that sort of general run-of-the-mill KC equilibrium style question you get at A level, where you're essentially being asked to work out KC. Those questions were you were given the KC and you're asked to work out other variables like mass, number of moles, or concentration of a reactant or product at equilibrium, or indeed at the start of the reaction. This question is kind of similar in that it's not your standard thermodynamics calculation. It's a little bit left field, and so it hasn't come up really very often at all. So it's a good idea that you make yourself familiar with it and the technique on how to do it. So as I said, it's a little bit odd, a little bit different than the other ones. So if it did pop up again, it'd be a real shame if you hadn't checked out and made yourself familiar on how to actually go about doing it. Now, it's only really the last part of the question that is difficult. The rest of it's a fairly standard run-of-the-mill thermodynamics question, and you'll see when we get to the last part how it's a little bit more challenging. So this question, it's about the industrial manufacture of iron in the blast furnace, and it's about thermodynamics involved in that. So you can see there are two methods for industrially making iron in the blast furnace. One of them is on the board, which you would be familiar with from GCSE, and it gives you some thermodynamic data about it. It tells you that the delta H, you can see here, is minus 24.8. Okay, and it tells you that the delta S is positive 15.2. Now remember, delta S, generally we will, if we're going to process this in a delta G calculation, which we may well do, okay, is given in kilojoules. Remember, this is given in joules. So if I would just kind of like to convert that straight into kilojoules just to remind myself, if I was you, what happens later. So we'll go through the start of the question, which, as I said, is pretty run-of-the-mill, and then we'll get to the rest of it. So first thing is define feasibility. Well, according to your specification, feasibility is very easy to find. It's simply a reaction in which delta G is less than 0. That's all it is. Explain why this reaction is feasible at all temperatures. Well, any reaction, I think all they'll be after here is you saying that the delta H is negative and that the delta S is positive. And if you have that, therefore, delta G is always, has to be negative. And you've already said up here, anything time that delta G is below 0, it is feasible. The reaction is feasible. If you're asked a little bit more detail about that, just remember, guys, delta G equals delta H minus delta S. If delta H is negative, which it is, and delta S term is positive, which it is, then the minus T delta S term has to be negative. Well, if both of those terms are negative, well then delta G can only ever be negative. It doesn't matter what the temperature actually is, okay? That's always going to be a delta G which is negative. So that reaction has to be feasible at all temperatures. Right, the next thing is then we're going to be asked to look at another reaction in which we can make iron in the blast furnace. And this is reduction with carbon this time, as opposed to carbon monoxide. And the first thing we're asked is about some of the information that's given in the table, where we're given enthalpies of formation for the various different reactants and products that are in the equation. And it asks us, why are the enthalpies of formation of carbon and iron 0? Well, that's very simply that the enthalpy of formation is defined as the enthalpy change when you make 1 mole of a substance from its elements in their standard states. Well, that would be making iron solid or carbon solid from its elements in its standard states, which is iron. So the enthalpy of formation for any element is always 0 because there is no energy change involved in that reaction. Okay, so your answer to that would be is that iron and carbon are elements in their standard states. It wouldn't be good enough just to say that they are the elements. You would have to add that they're in their standard states. Okay, we've now got to do a bit of calculating. So we've got to calculate the enthalpy change for the reaction that was on the previous screen, and then the entropy change for the same reaction. So let's calculate the enthalpy change for it. First of all, we're given enthalpy of formation. Now, there's a couple of ways to do this. I'm going to do it the long way and I'll do it the shorthand way. Okay, so I'm going to write out the equation first, because the long way we have to draw out a Hess's law cycle. And this is just in case they do ask you to draw a Hess's law cycle. It's not a bad idea to go over it and just remind yourselves. So when we're working out the delta H, so we don't want to work out the delta H for this particular reaction here, and we're given enthalpy of formation data in the table. That means that our intermediates have to be the elements in their standard states from which the reactants or products are made. So that's 2 iron solid plus 1.5 O2, which are gas, plus 3 carbons, which are solid. The delta H is the enthalpy of formation, so I'm forming that. So my arrow has to go towards the iron. My arrow has to go towards the carbon, towards the iron oxide, I should have said first of all, and towards the carbon monoxide. We're forming, so they go towards the things that are in the table. Now, we're forming 1 mole of iron oxide, so that's minus 824. Sometimes people multiply it by 2 because of the 2 down beside the iron. It's to do with the number of moles of iron oxide you're making, not the number of moles of iron that it comes from. These two here are 0. I drew them on anyway, but they're 0. Okay, and the final one, we're making 3 moles of carbon monoxide, so that is minus 111 multiplied by 3. Okay, right, if you remember then, any time that we draw a Hess's law cycle and we have an arrow going against us, we take it away. So we are starting here and we want to go to there and work out that energy change, that delta HR, if you like. Okay, the arrow in the minus 824 is going against us, so we do 3 times minus 111 minus the minus 824. Okay, now that's one way of doing it. The other way to do it, if you're given enthalpy of formation data, okay, so the delta HR, enthalpy of formation, very simply is the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants. And that's the quick way to do it without having to draw out a complete Hess's law cycle. But sometimes they do ask you to draw the Hess's law cycle, so it's not a bad idea to make sure that you can do that. Okay, so if we do all of that, the answer comes out at positive 491, and remember that is kilojoules per mole. Okay, so the answer to this is positive 491 kilojoules per mole. The next thing they ask us to calculate is the entropy change. So we're going to go to the next column across in the same table, but we're going to go to the entropy values. Okay, so remember entropy, change in entropy, or delta S, is equal to the sum of the entropy of the reactants minus the sum in the entropy of the products. So let's just do that very quickly. Reactants, first of all, we have iron oxide and we have copper. So iron oxide, we have 1 of those. Sorry, not copper, carbon, I should have said. And we have 3 of those. So those will be our entropy values for our reactants. And then for our products, we have iron, we have got that times 2. And we have carbon monoxide, we have 3 of those. That will be my entropy of my products. So if I do all of that, I will end up with my reactants come out at 696.6 minus 104.5. So my delta S comes out a positive value, 592.1. And remember, those units are joules per Kelvin per mole. Okay, what I would always do here when you're doing entropy value is have a look at the entropy and just decide yourself before you do the calculation, does it look like it should be positive or does it look like it should be negative? Well, here we're going from 1 mole, 4 moles of solid to 2 moles of solid, but most importantly, 3 moles of gas. So this should be a large increase in entropy, so a positive change, and that's exactly what we've got here. So we can be fairly confident that we can move on then to the next question. So that is positive 592.1, and that is joules per Kelvin per mole. Right, now the difficult part of the question that caused most challenge. So it's not too bad, but it is, if you're mathematically not quite on the ball, you might find it a bit of a challenge. So what they've asked us here is calculate the temperature at which the value of the standard free energy change for both reactions is the same. Okay? Now, in other words, what they're saying, delta G is equal to delta H minus T delta S. So what they're saying is for both reactants, tell them at which point those two are equal. So in which point are both delta H minus T delta S and one equal to delta H equals minus T delta S and the other. Okay, because both of those calculations, if I do them, are equal to the delta G. So I've got to work out the temperature at which both of these values, the outcomes of these two formulas would be exactly the same. In other words, at which point the delta G would be the same. Okay? So we have, if we go right back to the start of the question, we were given this information here. We were given the delta H and the delta S of reaction number 1. And then we worked out the delta H and the delta S of reaction number 2. So I'm just going to put these up here. So if we call reaction 1 R1 and reaction 2 R2, we worked out the delta H and we worked out the delta S. So for R1, the delta S came out at 0.0152, and I've converted that into kilojoules, you'll notice, because the delta G equals delta H minus T delta S. The delta S should be in kilojoules, so I've just done that. Okay, and the delta H for reaction 1 was minus 24.8. Okay, and reaction 2, that's on the board, that's 491, and this is 0.5921. Again, 592.1 divided by 1,000. So what we're basically saying here in both instances, if I just go down to the bottom, we're saying that minus 24.8, okay, minus T delta S. So delta S is 0.0152. Okay, so 0.0152 T, or T delta S, is exactly the same thing. In this case, has to be equal to 491 minus 0.592 T, okay, or T delta S. It's the same thing, okay. I just arranged it, called it 0.0152 T and 0.592 T because it's kind of more algebraic language, if that makes sense, and makes the whole thing a little bit easier to solve. So let's start flicking things about here, okay. So we have got minus 0.0152 T plus 0.592 T equals 491 plus 24.8. Okay, hopefully you can all see, fairly straightforward algebra there. So that means that 0.5769 T is equal to 515. Therefore, if I take my 515 and I divide it by 0.5769, that is equivalent to T, and that tells me that the temperature at which the delta G is equal in both of these reactions would be 892.7 kelvins. Okay, so that was a tricky one. The last part, as you say, which is worth 2 marks, was the tricky part. The rest of it was pretty standard, and most of you should be able to work your way through the rest of it. Have a look at that. If it crops up again, fantastic. If not, well, something similar might crop up, and if not, well, maybe your algebra has improved a little bit. Okay, all the best.